So I guess we'll go ahead and get started. My name's Ed Kelley, and I'm going to be talking a little bit about our work with interactive venue maps at SeatGeek. More specifically, I'd like to talk about how we made our maps both easier to use and 10 to 100 times faster by using spatial data structures and HTML5 canvas. So as I said, my name's Ed Kelley. I'm a full stack engineer at SeatGeek, and I'm primarily work on venue mapping technology. And so what I kind of want to do here is just walk you through basically the last year of work we've done on our maps. And we've gone through 2 major iterations, and I think we've found some pretty interesting solutions to some tricky problems. And so I'm just kind of go through what we found. So for those who aren't familiar with SeatGeek, SeatGeek is basically a search engine for tickets. So we aggregate the secondary market primarily and have a lot of really cool features such as interactive maps, view from seat images, and a deal score, which is basically ranking deals based on historical data. So if you were to go to SeatGeek.com, you'd see something like this. This is, I guess, a Yankees game, and it basically shows a big interactive map with a bunch of markers on it that represent the deals that are available at that game. So green dot would be a great deal, red dot would be a bad deal. But the kind of main thing you take away from here is the map is kind of the core interaction element on our page. So it's very important that it's both easy to use and also very, very highly performant. So the way this works is you basically can click on any section or really any marker, and that would update what information is viewable on the left side of the page. And you have the view from seat image there. So a little bit about how they work. We use a fantastic library called Leaflet. If you've ever used interactive maps before, Leaflet's kind of the go-to today. And the way Leaflet works is based on your zoom and pan positions of the map, it requests raster image tiles from the server. So if in our use case, if you're zoomed in at like a zoom level 0, that represents 1 tile, or the entire map fits in 1 tile. Zoom level 1 is a 2 by 2, and so on and so on. And so our maps consisted of several different layers. Our bottom layer was the image layer. And those were the image tiles that were brought in by Leaflet and stitched together. And that kind of includes the field image, the section, the labels, everything like that is in the raster layer. On top of that is the SVG outline. And we show an SVG outline on top of the section that you have either highlighted or selected. On top of that is the marker. The marker shows kind of the quality of the deal, and those are basically like image sprites. On top of that is a pop-up that we show a little bit extra information. So the issue is, let's say we want to hit that marker right over there. It's about a 10 pixel by 10 pixel area, and there's a few hundred of them on the screen, and it really makes the page feel like this. This is not how you want your UI to be. So how do we make this experience of clicking around on a map to find the best deal at a sports game better? There's this concept in Fitz's law, or in HCI called Fitz's law, which basically says that the time required to hit a target on a screen is dependent on both the distance to that target and the size of the target. So to make our page easier to use, we have 2 options. We can either decrease the distance to try and hit one of those markers, or we can increase the size of that marker. Now the thing is, on maps, you can't really rearrange things to make every single marker easier to hit. So what we're going to look at is how do you increase the clickable size of a marker or a section. So if we look at our maps, kind of one potential thing you could do is just make the clickable area of a marker larger. Just say if the dot is radius 10 pixels, make its clickable area 20 pixels. Problem is that you get into some pretty weird situations with that, where you have like overlapping clickable areas. And it's also just not a very intuitive way to interact with something. But a more natural way to interact with this would be able to, let's say we can click anywhere in the section that that marker relates to. And that's a very natural thing to do. I want to send section 203. I should be able to click anywhere in that section to select it. So our first attempt at doing this would be Well, we have all of these SVG outlines for all the paths. These are already being passed to the front end. And we're showing them only when you hover over a marker. But what if we drew every single SVG path at once? So we have all these sections. We draw them on every single, we have all these SVGs. We draw them on every single section that's on the map. And then we let the browser basically do the work for us. So when we hear an event, a mouse over, a mouse click on an SVG, we know to select that marker. And so they'd be basically invisible to the user, but we'd use them for events, which seems pretty reasonable. But we have a problem. And this problem looks kind of like that. That's Yankee Stadium. Yankee Stadium has 387 sections and just about 3,000 rows. Browsers do not like drawing that many SVGs on the screen at once when you're trying to pan and zoom them and really just move them around. So we had to scrap that. So our second attempt at doing this is something called Polygon hit testing, which is used a lot in things like games or computer graphics. So we already have these SVG paths that just define the shape of the sections. So instead of trying to put a bunch of SVGs and then let the browser do the hit testing for us, why don't we kind of turn it around and listen to the mouse event and then figure out, does this mouse event fall within the polygon that is the section? So the key to this is we need to be able to do this check very, very quickly, because we're getting all these mouse events in, and we need to be able to very quickly say, does this mouse location fall within a shape on our map? And the way we do this is by using something called an R tree. Now, an R tree is a spatial data structure that's really good at looking up, does something fall within a bounding box, or do two bounding boxes intersect? And this is kind of the Wikipedia diagram of it. If you're familiar with binary search trees, it's a pretty similar concept. The basic idea is that you can very quickly eliminate large areas of the search space when you're searching for a bounding box. So this can very quickly say, okay, given a point, which bounding boxes does this intersect, which is important for us. So our algorithm looks something like this. On our map load, we get all this data that describes the SVG outlines of the map shapes. We go ahead and convert those to polygons, so basically just lists of points. Then we calculate the bounding boxes, or just the extents, or the min x, min y, and max x, max y. Then we insert those bounding boxes into an R tree, where kind of the key is that bounding box, and then it has a reference to the marker that it relates to. And then for every mouse event we get, or a buffered series of mouse events, we convert the screen to map coordinates. So when you get a mouse event, that mouse event is going to be in the coordinate system of the screen. But what we need is the coordinate system of the map, which in our case is 0 to 1,000. But you could see in a normal geospatial application, it's a lot long. But there's some sort of mapping function that goes from screen to map, and that is dependent on your pan and zoom and the position of the map on the page. So we do that conversion. Then we say, which bounding boxes does this mouse or map position intersect? And we do that by looking it up in the R tree. And then we get a couple candidates where sometimes the bounding boxes will be overlapping with where the mouse position is. So then we do a kind of more expensive check. Instead of bounding box, we actually check, is this point in the polygon, not within the bounding box? And then eventually that will give you, which polygon does this intersect? And then you can use that information to then highlight the marker. And so that looks something like this. You'll see, the mouse can move around. As soon as it enters into the section area, we can trigger the hover event. And so we're able to do this, and it happens on rows as well. We're able to do this, and it has basically no negative impacts for performance, and it makes our maps way easier to use. So that's great. So that was kind of our first iteration. But there's still some remaining issues where we were still having frame rate issues. And then also the event handling was getting pretty complicated because we were doing R tree lookups, but we were still looking up marker events. And if you hover over a listing, we highlight the shape. So there are a lot of boundary cases that was just like insanely complicated to keep track of. So the main thing we're going to try and fix is the first one, to get this frame rate up. Because we were hitting maybe like 35 frames a second, 25 on a lesser computer. For some reason, on a recent version of Firefox, it dropped down to like 20. So it just kind of felt a little slow and just not a great experience. So the key we found to performance is how do you reduce the number of DOM elements that the browser has to just move around, because the maps are moving around, and you need to just decrease the number of things the browser needs to worry about while drawing it. So a common way to do this in maps is to do clustering. Now, this is the Leaflet marker cluster plugin. The thing is, this works very well for geospatial things. You know, you're in a city, you can kind of consolidate nearby things into one marker. That doesn't work in venue maps because position on the map does not always lead to a great grouping. For example, you would not want to group together VIP box and upper level sections at Yankee Stadium. People would be kind of upset about that. So this doesn't really work for our application. So instead, what we're going to do is, instead of what we had before, which is where we have a marker, then an SVG, then the image layer, we're going to combine the marker layer and the SVG layer into a single HTML5 canvas layer. And what we're looking to do here is we want to minimize two things: the number of DOM elements being moved around, and also the frequency that you have to redraw these canvas elements. So we kind of have two options here. First option is to have a static canvas element. The static canvas element would basically be the entire size of the screen for us, because our maps are full screen. And this would basically stay in place, and the map would kind of move under it. So the map tiles, if you panned, would move under the static tile canvas element. But what you have to do then is you have to redraw the position of the markers every single, like at a 60 frame rate time. So you have to basically constantly be redrawing the markers and the outlines and everything anytime you do any sort of movement on the map. So while this really does drop down the number of DOM elements, it really requires a lot of redrawing. So our second option, and the one we went with, is using tiled canvas elements. So just like we have tiled images for the maps, basically on top of each tiled image, we draw a tiled canvas element. And so what this lets us do is that it lets us to kind of balance these two things. We reduce the number of DOM elements, not as much as a single canvas element, but there'll still only be a handful on the screen that the browser has to move around. But it also lets us really drop down the frequency at which we have to redraw things. So that looks something a little bit like this. I've turned on kind of a dark color so you can see where the canvas elements are with a little bit of buffer. And so the idea here is, let's say you move the map 50 pixels. That doesn't have any new tiles come on the screen, and it doesn't have any new drop off. But what it does is the browser can just do a CSS transform on all the tiles, which it's very, very fast at. And then none of the tiles actually need to be redrawn. And the great thing is Leaflet can actually handle when you move tiles off the page. It knows it doesn't need to worry about them anymore. And then it knows, oh, I need to draw some new tiles. So you get this really nice balance where you only have to redraw tiles when it's absolutely necessary, and otherwise you're using CSS transforms to move the map around. And this is kind of how it looked, kind of split up at a much higher zoom level. So our process looks something like this. To first draw the tiles, well, first of all, we put all the markers into an archery, because we love those. And we calculate the map bounding box covered by the tile. So basically, Leaflet says, OK, I want you to redraw this tile. And this tile has a position and a zoom. And so given that information, we figure out, OK, in map space, what bounding box does that cover? And so we look up, give me all the markers that are held within that bounding box, which is a very, very fast lookup. Then we only draw exactly those markers to that tile. So we've added a small buffer, because you get into some corner cases where if a marker is just outside the tile, it should kind of come into the tile. So you add a buffer about the size of the diameter of the marker. But this lets us only select the markers that are necessary and very quickly draw them to the tile. And we do this for every tile as it needs to be redrawn. And then redrawing tiles. So we have a couple things that cause a redraw of tile, or a tile or tiles to need to be done. Let's say you hover over a section. Well, we draw a nice little outline along what section that refers to. So we need to let our redraw function know, OK, we need to redraw this tile. And so the way we do this is we keep track of a redraw extent between each redraw action we do. Because sometimes a couple different actions will happen between our last request animation frame and our next one. Like if you were to unhover one row and hover a next one. And so we kind of keep track of a union of bounding boxes that just expands as you do more actions on the page, which usually will only happen one action, but sometimes there's a couple grouped together. And then you calculate which tiles intersect with that kind of bounding box extent that you've calculated, and only redraw those tiles. And so I have some debugging on here, which basically redraws the tile with a new color for each redraw call. And you can see when you only need to redraw one tile, just that tile gets redrawn. But if the section covers two, it redraws both. And here's it on mobile. You could do this. There's a slightly faster way to do this. You could redraw only portions of the canvas. But the thing is, we are getting such good performance with this that the extra code complexity of doing like sub-tile rendering or redrawing just wasn't really worth it for us. So this is great. We're super happy with this. It performs well in all browsers. And then our designer says, OK, let's add drop shadows to the markers. It's like, yeah, I can do that. It's one line of code, no problem. Problem is, shadow blur on canvas is slow, like really, really slow, like 1,000 times slower than just drawing a marker. And so our solution to this is to do something we call buffered markers. So instead of redrawing each type of marker from scratch every time we need to draw it, we would draw these each once when the page load. So we'd create several off-screen canvases, or just really canvas contexts, and draw the markers once to those canvases. And so we could do very expensive things. You could do gradients, drop shadows, anything that our designers wanted, we could draw there, because we only have to do that once. And then when we actually need to draw that to a tile when it gets redrawn, we use draw image. Draw image is very, very fast. It's almost as fast, or it's basically as fast as just drawing a circle. And so this lets us kind of incur the expensive calls once, and then do very cheap calls for the rest of the page duration. And so yeah, here are results. This is the Chrome timeline. It's probably the best thing to look at. This is our old maps with the sprite markers. And we were getting 20-something frames per second, which just felt laggy. And this is on a new MacBook. And with the canvas markers, we're getting well over 60 frames per second, and it's barely using any resources on the computer. And kind of a neat side effect of this is because our markers are generated on the fly, we can describe them with code. So we can basically style them as if they were with CSS, which is pretty neat. If we want to change any sort of style on the markers, it will update on our next code deploy, instead of having someone go into Photoshop, designing the sprites, and deploying them again. And yeah, this is what all this kind of looks like together. You can see it's very fast. Looks to the user, you can't tell they're tiled at all, and it has great performance. So thanks. I'll take any questions. Any questions? Sure.
So was the first one that you did that didn't work, like the invisible Voronoi diagram for the SVG markers?
No, so the SVGs were actually the outlines of the sections. So that actually defined the shapes they were in. And then the browser gives you mouse events on those shapes. So it wasn't Voronoi, it's basically exactly those polygonal shapes. So the user experience was correct. It just, the browsers couldn't handle it. Anything else? Yeah.
So for your final approach, did you still have to kind of have like the SVG, like when SVG doesn't draw, or is it like the separate tiles that you have, or like the canvas tiles for like the stadium, and like performance impacts? So yeah. Like drawing the SVG elements inside the canvas versus using like actual SVG nodes for.
Yeah, so we were drawing those in the canvas. So we basically converted. So in our conversion step where we took the SVG and took it converted to polygons, then we just drew those outlines with basically the canvas path. So it was all in one layer. Everything was kind of baked into that canvas layer and the image styles. No, Canvas is super fast at drawing a small polygon. And I actually guess that's okay. Yeah, I have one more question.
Sure. So you have these SVGs that you download. Are they SVGs?
Yeah.
Are you getting any performance impact by having to download large SVG files?
So the SVGs kind of come on initial page load. It's reasonably large, but it's compared to the image tiles and the total amount of listings we're loading, it's a very minor part of the page. In gzipped, it's quite small. So I think that's actually all time. I'll be down here afterwards if anyone has any other questions. All right, thanks.